11.1, we're going to look at a chi-square test for goodness of fit. Okay, so the example we're going to look at is Carrie made a 6-sided die in her ceramics class, and she rolled it 90 times to see if each side was equally likely to show up. On a regular die, that's what it would be, but since she was making this herself, she wanted to see if she got it weighted and shaped correctly so that each side is actually equal. All right. So, the hypotheses for a goodness of fit test. The null hypothesis is that the sides of the die are equally likely to show up, and the alternative is that they are not equally likely. So you can write those words, that is perfectly acceptable. You can also use some mathematical symbols. So our null hypothesis is that the proportion of getting each number, 1, 2, 3, 4, 5, 6, is they are all equal to each other. And then our alternative is that at least 2 of those proportions are incorrect. And if you're going to do that, if you're going to use symbols, then you have to define your parameter, of course. And so P number would equal the true proportion of times Carrie's die length on that particular number. Okay, so either way, you want to write these symbols perfectly acceptable, you get to choose. One thing we want to note, though, is we want to make sure that our alternative hypothesis doesn't say that all of the proportions have to be wrong. Okay, some of them could be, the equally likely proportion that we assume. But if 2 or more of them are wrong, that's what we're looking for in that alternative. So make sure you don't write that like all of them are not what we expect them to be. All right, so Carrie rolled her die 90 times. And she recorded how many times each number came up out of the 90. A question that we need to know when we're doing a chi-square test is what is those expected counts? How many times would we actually expect each number to come up? And so in this case, because we are assuming that each number is equally likely, we could do 90 divided by 6, which would give me 15. So I would expect each number to come up 15 times. The other thing that we could do is we could multiply the number times the probability of that number happening. That's just a different way of doing the same math. Expected counts do not need to be whole numbers. They can be decimals. So, if she had rolled it 95 times instead, those expected counts can be decimals. All right, and so as we see, not all of Carrie's numbers totally matched up with that 15 that we expected. In fact, only 6 came up exactly 15 times. So we want to know how likely is it that these differences that we came up with would occur by chance? Or do we maybe say that Carrie's die is not fair? Okay, and the statistic that we're going to do use to make this comparison to figure out this number is called a chi-squared statistic. Okay, this is the Greek letter chi, C-H-I, but it's pronounced chi. That is the statistic that we are going to calculate. And so the way we find it is the sum of, remember this is the Greek capital letter sigma, so it's the sum of, for each category, so in this case for each number on the die, the observed count, how many times it actually happened, minus the expected count. We're going to square that and then divide by the expected count. We're going to do that for each number 1 through 6, and we're going to add those together. So the number 1 actually came up 12 times, and we expected it to come up 15 times. The number 2 actually came up 28 times. We expected 15. So we do that for each number 1, 2, 3, 4, 5, 6, and add those all together. And so the value of our chi-square statistic, tongue twister, is going to be 14.41. Okay. What we're going to do with that is similar to what we did with our Z test statistic or T test statistic. We're going to use that to find a p-value, the probability of getting that a number greater than or equal to the chi-square that we got for our sample. And to do that, we have to use a chi-square distribution. So when we did Z, we used a normal distribution. When we did T, we did a T distribution. Okay, so when we find chi-square, we're going to use a chi-square distribution. Okay, things that you need to know about chi-square. it is only non-negative values because every problem that we're going to be doing with a chi-square distribution, we're going to be counting things, and we can't have negative counts. This is a distribution that is skewed to the right, and just like our t distribution, we're looking at degrees of freedom here. The higher the degrees of freedom, the less skewed it is. So if you look at like that red one, that's degrees of freedom of 4. It's sharply skewed. And then if you look at the degrees of freedom of 8, it kind of flattens out a little bit. It's still skewed to the right, but just not as much. And so these are some characteristics of chi-square test. Like we talked about, it becomes less skewed as we increase the degrees of freedom. And then the mean is equal to the degrees of freedom, and then as soon as we get above 2 degrees of freedom, the mode is equal to degrees of freedom minus 2. Okay, so just some characteristics that you need to know. We are going to use our calculator to find the p-value of our chi-square distribution. So just like we did normal CDF and t-CDF, this time we're going to use chi-CDF. Okay, degrees of freedom is always the number of categories that we have minus 1. So in this case, Carrie's die has 6 numbers, so 6 minus 1 is 5. Okay, and you see the calculator directions on your screen. All right, so now that we know what the chi-square distribution is, we can use it to conduct a hypothesis test, okay? Just like before, we got 3 conditions: random sample, 10% condition, making sure our sample is less than 10% of the population, and then for the large counts, all of the expected counts have to be at least 5, okay? When we do any chi-square test, we are going to write out all of the expected counts, and then write a statement saying that all of these are greater than 5. Okay, so you have to make sure that you write out all of the expected counts. You do that math and figure out what each number should be, and then also state when it meets the large counts condition, because all of them are more than 5. Okay, so chi-square statistic, same as what we just talked about, and then the p-value is the area to the right with k minus 1 degrees of freedom. Okay, so let's look at an example. You can pause and read through this example. All right, so first thing we need to do is write our hypotheses. So we would assume the null hypothesis is that the birthdays are uniformly distributed across the 4 quarters, and then our alternative is that they are not. Okay, and they didn't give us a significance level, so we will just use 0.05. Okay, so plan, we are going to do the test we're going to do is a chi-square test for goodness of fit. You need to make sure that you write that, especially if you're going to use your calculator for anything, so that we know what test you are doing. So when we check our conditions, random condition, they said it was a random sample. 10%, we're going to assume that 80 is less than 10% of all NHL players. And then for our large counts, our expected counts for this are all going to be 20. All right, because we have 4 quarters in a year that we're going to divide those 80 people up, and then 20 is greater than 5. Okay, so then when we get to the do part, we are calculating our chi-square test statistic. Okay, so again, for each of those, it is observed minus expected squared, divided by expected, and then we add them all together. Our degrees of freedom in this case is going to be 3, because we have 4 categories. The 4 quarters of the year minus 1 is 3, and then you would use chi-squared CDF to find the p-value. All right, just like with all of our other tests, we can also use the calculator. If you're going to do that, which is totally fine, you need to enter the observed counts in list 1, so the data from the problem, and then the expected counts in list 2. And then I would also write those expected counts on your paper. Okay, and then make sure you report, again, the chi-squared value, the degrees of freedom, and the p-value from the calculator in your answer. All right, and then same conclusion as we've been doing, because the p-value is less than 0.05, we reject the null hypothesis. So we can say we do have convincing evidence that the birthdays are not uniformly distributed across the 4 quarters of the year. All right, so always a reminder about the calculator. If you choose to use it, totally fine, as long as you make sure you write things down. Okay, so report the test statistic, the degrees of freedom, and the p-value. Okay, now, when we get a test that says that our distribution is not the expected, okay, so when we reject the null hypothesis, we need to do a little follow-up analysis just to see how it is different. And so what we're going to look at is what are the categories that had the biggest contribution to the chi-square statistic. So when we did our math, which was the biggest numbers? Because the biggest number means the difference between the observed and expected was the largest. Okay, so in this case, the first quarter of the year and the last quarter of the year had the biggest difference. Okay, and so in the last quarter of the year, the younger players, we had 8 fewer than expected. And in the early part of the year, we had 12 more players than expected. And so that would tend to agree with kind of the reasoning that was laid out in the problem, is the guys that are older get more opportunities. Okay, and that is it for our chi-square goodness of fit.